Okay, in this video we are going to go over number 6 from the 2017 Calc BC exam, and it is the series question. It's kind of a strange series question, a little bit. So first off, we're given that f of 0 is 0, f prime of 0 is 1, and then the n plus first derivative at 0 is equal to negative n times fn, the nth derivative, at 0. So it's like you always go back one step, and that's going to be important. So we're also told that all derivatives of all orders exist for x between -1 and 1, and that the Maclaurin series for f converges to f of x when the absolute value of x is less than 1. But pretty much none of that's relevant for a while. So the first thing we're going to do is show that the first four non-zero terms are the terms that were given in the problem. So you're actually given x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. And then we want to write the general term of the Maclaurin series for f, which means it's centered at 0. So I'm going to start off by making a table. So I'm going to go 0, 1, 2, 3, 4, and then it's n, and then the nth derivative. So you're given the 0th derivative, which is the original function. You're given the first derivative, so you're given 0 and 1. And now when you hit n equals 2, that means you go back to 1, and you do -1 times the first derivative, so you get -1. When you hit 3, it means you go back to 2, and you do -2 times the second derivative, which gives you +2. When you get to 4, you go back to 3, and you do -3 times the third derivative, which gives you -6. So that's how you kind of fill these in. I think that's all we need because that'll give me 4 non-zero terms. So now what I'm going to do is I'm going to just kind of write out the generalization of Taylor's formula, which is 0, the function at 0, the first derivative, 1 factorial x to the first, plus the second derivative over 2 factorial x to the second, plus the third derivative at 0 over 3 factorial x cubed, plus the fourth derivative at 0 over 4 factorial x to the fourth, and then I'm going to say plus ... And now I'm just going to fill in. And so remember, I'm just trying to match something, so I already know what the answer is here, which would give me a good hint if I was going wrong. So I'm plugging in 0 there, and then I have 1 over 1 x to the first, plus it's going to be -1 over 2 x squared. So I'm expanding the factorials to match things. And then it's 2 over 3 factorial, which is 6, x cubed, and -6 over 24, x to the fourth, and I'm going to go plus ... because eventually I need to generalize. So this, if I simplify, it's going to give me just x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. I'm going to go plus ... again. So I already matched the 4 terms, so I've accomplished that goal. And now I'm going to generalize this thing. So it looks to me like I can say every odd power needs to be positive, so I want a -1 to the n plus 1, and then that's just going to be x to the n over n plus ... So that should do it. And now we're going to move on. We're actually going to use this, but we're going to move on to part B. So in part B, we want to decide when we plug in x equals 1, do we get a series that converges absolutely, converges conditionally, or diverges? So this is a new concept to the exam in 2017, the idea of absolute convergence. I think it used to be on the exam a really long time ago, so if you're looking for practice, go way back into like maybe the early 80s or earlier even. So let's see, if I plug in 1, so I'm going to start there. I get 1 minus 1/2 plus 1/3 minus 1/4. This is the alternating harmonic series, which is very famous, but I'm not entirely sure if you're just allowed to outright state alternating harmonic so it converges. So instead, I'm going to show that it converges by the alternating series test. So I'm going to say this has terms that, so there's kind of 3 things. So first, they alternate. They decrease in magnitude, and then they have a limit that is 0. So that means that they this series converges by the alternating series test. So this converges by the alternating series test. Now what I'm going to do is I'm going to take the absolute value of each term and see what happens. So instead of having 1 minus 1/2, I'll have 1 plus 1/2, plus 1/3, plus 1/4. So if I do that, I get this, which is definitely the harmonic series, which I think I'm allowed to just say is a harmonic series and therefore diverges. So that's what I'm actually going to say. If you're not allowed to say that, I guess I would say it's a p-series with p equals 1 and therefore it diverges. It's kind of wishy-washy at this point what you're allowed to say, but I think this is good enough. And so it converges when it alternates. It diverges when you take the absolute value. So that's what it means for it to be conditionally convergent. So combine that information, we have this is a series that converges conditionally. And so this is taking forever to write. Converges conditionally. And let's move on to part C. So part C is a much more traditional question. G of x is the integral from 0 to x of f of t dt, and I want 4 non-zero terms and the general term. So what I like to do is just replace f of t with the Maclaurin series. So it's g of x is really the integral from 0 to x of the quantity, and then it's t minus t squared over 2 plus t cubed over 3 minus t to the fourth over 4, blah, 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 and then dt. So I'm going to go through and integrate this power rule each individual term. So that's going to give me, so I get 1/2 t squared, and then minus 1/6 t cubed, and then plus 1/12 t to the fourth, minus 1 over 20 t to the fifth, and then the general term, the only variable is t, so that becomes t to the n plus 1. The other things just stay the same, and then divide by n plus 1. And we need to evaluate this from 0 to x. Well, plugging in x just changes all the variables to x. Plugging in 0 changes everything to a 0. So when we evaluate this, we get that. And that actually, yeah, that's the answer to part C right there. So that's g of x. And part D I'm actually just going to squeeze in here. So part D, we're told that p sub n of 1/2 is the nth degree Taylor polynomial about 0, which means just plug 1/2 in for x in the answer that you got. And we want to use alternating series error bound to show that something, p sub 4 of 1/2 minus g of 1/2 is less than 1 over 500. So what I'm first going to do is I'm just going to state that it's a convergent alternating series when I plug in 1/2, because I'm not 100% sure that I'm allowed to just dive in, so when in doubt, I kind of over-explain. So I'm just going to say p sub n of 1/2 converges by the alternating series test. Therefore, so if it's convergent alternating, I know that the error term is at most the first term left off. So it's going to be less than the, it's really the magnitude of the first term left off. So p sub 4 means go to the fourth. So I'm using the x squared, the x cubed, the x fourth term. So I'm plugging 1/2 into the x to the fifth term. So it's less than the absolute value of negative 1 over 20, and then 1/2 to the fifth. And then 1/2 to the fifth is 1 over 32, and 32 times 20 is way bigger than 500, which means that this is definitely less than 1 over 500, and that's what I needed to show. So that's the series question for this year. I hope you found this helpful, and good luck.